1.4. 1.4 functions can also be combined. The domain of the arithmetic combination consists of all real numbers that are common to both the domains of f and g. And in the case for the quotient, there are restrictions, because when you have a quotient, you can't have 0 in the denominator, so you would say the function cannot be equivalent to 0. This comes from your box, but pretty straightforward. When you're adding them, we get a sum, subtracting is a difference, product when you multiply, and the quotient when you divide. So if I'm going to find the sum of my functions, I literally just add them together. 3x plus 1, let me get a better color here, plus 2x squared plus 2x minus 1. We put things in the proper order. Largest exponents go first. Combine our x terms, and then the ones cancel each other. So when I evaluate their addition, well, I know what their addition is because I just did it. So all I have to do is substitute in the 2. This is their addition, so I can substitute in 2. If I want, I could substitute 2 into each of them and then add that together, but I get the same thing. 2 times 4 gives me 8, and 10 for a total of 18. The domain of f, when I look up here at f, this is a line. A line goes forever left and right, so it is all reals. The domain of g, well, g is a parabola. The parabola goes forever left and right, because that's what domain is, x values. So it is also all reals. So the sum is the reals and the reals. Well, all the reals together still give me the reals. Okay. Page 2. When I'm subtracting, I need to be a little bit more cautious, because when I am subtracting a function, I need to remember that I'm subtracting all parts of the function, not just the first part. So when subtracting, I do have to subtract all pieces, which means distribute that negative. Then when I put things in the proper order, highest power to lowest power, combining the like terms, I get negative 2x squared plus x minus 1. When I substitute in 2 at this time, again into their difference, so just minus 2, 2 squared, plus 2 minus 1, minus 2 and 4, minus 8, minus 6, we get minus 7. So the domain, again, of a line is all reals. The domain of the quadratic is all reals. So their subtraction is still all reals. Product of multiplication, we're just going to be multiplying the functions together. They mean the same thing. Multiply one function together. This is just another way to write the exact same thing. And I could have done that up here. I could have said f of x minus g of x. They mean the exact same thing. I'm taking one function, subtracting the other, one function, multiplying the other. So in this case, I get x squared minus 1 times x minus 3. Distribute, so we're going to get x cubed minus 3x squared minus x plus 3. There's no combining like terms. Everything is in order. So when I'm going to evaluate, I'm just substituting in the 2. 2 cubed, 2 squared, 2. So I get 8 minus 3 times 4. So 8 minus 12. So negative 4 minus 2 plus 3 is negative 6 plus 3. and then minus 3. So evaluating usually is done after you do the combination of whatever it wants to do. Add them, subtract them, multiply them, whatever you have there. All right, difference is actually the wrong word that should be written there. It should say quotient, because we are dividing. Whether f is divided by g or g is divided by f, what's important is that we don't have 0 in the denominator. The first thing it's asking, though, what is the domain of f? If the f function is the square root of x, remember to find the domain of the square root is to put the underneath greater than or equal to 0. So the domain of the f function is 0 to infinity. Again, interval notation, just kind of refreshing our memory of what we did previously. So the domain of the g function means we're setting what's underneath greater than or equal to 0. When I solve this, I subtract the 4, get rid of the negative, and now I'm going to get plus minus 2. And when I do this, it's actually x is less than or equal to 2. Because remember, when I square root, I'm going to get two answers. I'm going to get a plus and a minus 2. Well, the plus is not going to change the sign, but the minus will. The minus that you get from the square rooting of 4 will change that sign. So the domain is everything greater than negative 2 and less than positive 2. So negative 2 to 2. That's how you're going to find the domain of a quotient there. Page 4, composites. Composites, notice the look of them are different. Here we have a function of a function. And what that means is we are substituting one function into the other. If I had f of 2, I'd put 2 into my f equation. But since I have f of g, I'm going to put the g equation into the f. That's what that is going to represent. Well, g is x plus 1. So that's what they did here. All they did was change g to the equation. And so they're putting the g equation into the f, and that's the result. So we would read this as f of g. It's read f of g. The composition, another way to write f of g is with this little open circle. And it's right in the middle, because if it goes too high, then it's considered a degree mark. And if it's closed, then it's a multiplication mark. So it's this little open circle that goes in between the two letters of the functions you want to use. But this notation is exactly the same, and you will see it both ways. So make sure you're very familiar with both of those. All right, so here we have f of x, g of x, and it says we want to find f of g. So that means we're going to put the g into the f. We're going to put g into the f. So 4 minus x squared, that's the g, into the f. Put things in the proper order so that we get negative x squared plus 7. All right, here we have f function is the square root of x. The g function is x minus 1 as long as x is greater than or equal to 1. And for the square root, the stipulation is that x is greater than or equal to 0. Those are just restrictions. So if I'm going to find f of g, I'm going to put g into my f equation. G into f. So the square root of x minus 1. Done. Now I've already done the composition of f of g, so now I'm going to substitute in the 2. So 2 minus 1, square root of 1 is just 1. And if I do it for 0, I get 0 minus 1, negative 1, square root is undefined. We cannot do that. I mean, it's imaginary, but we're not going to go that far. We just say it's undefined. All right. To find the domain of a composite function, you need to restrict the outputs of G so that they are in the domain of f. So we're going to find the domain of the composite f of g if we know f is x squared and g is a square root. Well, the first thing we need to know is the domain of each of them at the beginning. The domain of a parabola is all reals. For a square root, I set it greater than or equal to 0. When I solve this, I get negative x squared is greater than or equal to negative 9, x squared less than or equal to 9. Now, the positive part of this stays the same sign. The negative part is going to switch. So less than 3 greater than negative 3 tells me that's going to be my domain. So when I do f of g, and I put the g equation into the f equation, so the square root of 9 minus x squared, because that's what I'm putting into my f equation. Well, a square and a square root cancel each other out, and it leaves 9 minus x squared. Or if you want to rewrite it, you get negative x squared plus 9. As long as the domain has a restriction of negative 3 to 3. Because we put g into the f, and there were no restrictions on f, the g domain ends up being the domain of the composite. We put a restriction into an unrestricted domain. So therefore, when I find the composite is the restricted domain. Let's look at some more here. Here we have two functions. Both of them are lines because they're single x. Here I'm going to find f of g. So that means I'm going to put the g into f. So I'm going to replace the x with g. When I simplify this down, the 2 and the half cancel. The minus 3 plus 3 cancel, and it leaves x. Now I'm going to go the other way, g of f. That means I'm going to put f into my g equation. So I get 1/2, and then x is going to be replaced. Oops. Want that there, not. Let's see, 1/2 parenthesis. Sorry. There's my f minus the rest of my g. Okay? So we're going to get 1/2. 2x and plus 3 minus 3 goes away. The 1/2 and the 2 go away, and it leaves x. If you put f into g and g into f, and your result is x, we call these identity functions. You will be asked to prove that functions are identities, and this is how you're going to prove it. You're going to put g into f, and then you're going to do f into g, and you're going to come up with x each time. and that's how you're going to prove that functions have identities, or that they are identities of each other. All right, on page 6, it says we want to identify a composite function. So we want two functions that were put together in order to get h. And that's what that's saying. What do we do with f? What do we do with g so that together we get h? And you always want to start with the most simplest of basic things. If you see powers, make that a function. Make whatever the power is next to the other function. So if I make f of x 1 over x squared, again, if I'm going to make x minus 2 a function, because that's what's being squared, the only thing that's left over is the 1 over and the square part. So that means all of that was x. So that means g of x then is the x minus 2. So that, let's go to g of x, write it in proper notation. So that if I did f of g, I would put g into my f equation. Sometimes it's just a trial and error. There really is no, rhyme or reason and stuff, and there are some other possibilities. There are different variations to some answers. As long as you got the work and you can support it and you can check it and you can prove it, it's going to be fine. Now on the other page, what they have a graph up here, and the graph is just to show you that h of x has this this graph does have a domain restriction, and that domain restriction is going to be at 2. That x cannot be 2. So when we look at that on our graphing calculator, we're going to look at the h equation. Plug on the calculator. Y equals 1 divided by, and then x minus 2 squared. We get this kind of a U shape, but no matter how close in I get here, we're going to find that not this U shape, but these kind of curved shapes, they never touch, and they never touch at this point of 2. This is an asymptote. But the pictures themselves look something like that. Because if I look here, my domain cannot be 2. Because if it is 2, I'm going to get 0 in the denominator. So I'm everything except 2, or in my new notation, there's going to be my domain. Well, if I look back at my original domains over here, f domain, the only thing it can't be is 0. Over here, I have no restrictions because it is a line. But when I put them together, I do have a restriction because it is a fraction. A fraction will always have a restriction, and it is its own. So just because we may not have restrictions, or we may have partial restrictions, in the end, we do have to look at all pieces. We look at the beginning, we look at the end, and we determine that, in this case, that the restriction of 2 is the domain that we need to have. And really the only way we're going to do that is either look at the graph or solve this out, knowing we can't have 0 in the denominator. So that will conclude 1.4.